that's what they came up with, that black design at the bottom. So that is a splint that has been printed and used that is the same equivalent strength as a full cast. So you can see that the possible benefits. Their outcome measures are very across the board, are a bit loose, might be a term. So they're not that strong. Or another really interesting one, and this is thinking about the use of computer-aided design and printing and such, is that there is an app already out that you can either scan or put in numbers into a bit of software, and that will print out a flat piece of material, and then the flat piece of material has already got its insertion points for a thumb hole and for putting your Velcro straps through and things like that. So it is flat. It still requires the skill of the therapist to then go and mould it. So you end up with a splint that's been printed out, which is the materials that are flat up there, the green material, out of the printer, a flat piece, and then you heat it up and mould it. So that's available through an app, and these people have looked at both the process of doing that computer software, as well as then actually getting the material onto a person. It takes a bit of skill to then mould a splint, as you guys all have. This is an interesting one in regards to they were using plaster of Paris for a mallet cast compared to a lattice or a 3D splint or print, and just showing the differences between plaster of Paris and a plastic splint. Really interesting in itself of how they're managing mallet fingers. There were lots of reading and interesting components that internationally, when you read these things, you go, well, that's a different approach to doing things that we might do things here. So that bottom left corner of the A is how they manage mallet fingers with a plaster in that position. So anyway, the comparison between those two. So this splint here is showing dynamics, so they're using material that is flexible, and they created a cast splint that is able to bend. So you can think of your Sabos and those sort of branded dynamic splints, or for radio nerds or whatever else you want to make one, and you can actually print out a position. So all these things that you're seeing are printed out of a printer, not made out of a factory somewhere else. It's printed out of a printer. So we have the bending parts there that then hook onto the fingers. Again, early exploratory research, but showing that it can be done. This was a figure of 8 splint, sort of similar to what we've researched, but they did it through a means of actually plastering or casting the finger and then scanning that and applying the scan process through the computer software to create a splint. I'm not sure why they did the casting process, but they did, and they created a figure of 8 splint. So again, that was actually published in the Hand Therapy Journal. Interesting bit of research. So this just shows the variety of research that's out there for additive manufacturing and 3D printing. It's not the little Loughborough Uni being one of the main people out there a few years back from sort of 2016. That's not just them anymore. There's lots of people throwing their hat into the ring, which is a good thing, I think. And part of the process of it is the use of computer-aided design software. And this is a key component to creating a digital file or an image of a part of the body, and then going with it. So today I'm going to show you the use of that through some videos, and then talk it through as well. So there's lots and lots, if you want to have a bit of a look into these, lots of different types. There's pros and cons, and the ease of use of some really tricky things versus some not so tricky. The really good part about it is that you can actually look at the designs and test them out. And when I say test them, you can actually put force through them on the computer screen to see that they're strong enough to do what they need to do beyond just having a guess. So computer-aided design is the ability to draw, create, design, and even test out, as I said, the design process of making whatever you like in part, and in this case looking at splints. So this design on a computer, a bit of software, can take things to a whole new world. It means we're no longer restricted as such. So primarily there's 2 ways of creating splints using software. You can either sketch it or draw it, which I'll show you, or scan it and then manipulate that file or the image that you see. And as I say, I'll show you a couple of ways of doing that. So this video, which will look through. Here we go. So this is Fusion 360 design. It does require a little bit of a strong computer as such, so it has to have a bit of go about it. And basically this is me drawing circles, very interesting, and changing circles, even more interesting, but on some fancy computer. So basically I drew a circle, I was pretty good at kinder, so I stuck to it. So now I've just manipulating the size of it. This is all in millimetres, so I've just manipulated that to 20, or modified it to 25 mil, and then because I thought I was quite good at drawing a circle, I thought, why not draw a circle? So this is a very simple design process that I've gone to the same part, or same centre axis point, drawn another circle, and they're very excited again that now I've modified that circle to be about that size, and just getting the measurements. So the computer-aided design software allows you to draw lots and lots of different shapes. So if you do get into this, you'll be able to look at different shapes and sizes. So I've just manipulated that. So now I've got a 3 mil difference between the inner circle and the outer circle, which correlates pretty nicely to some of the material that we use. And now I'm doing a little bit of a push method, or extruding the design, making it bigger. And in a second, when I get my mouse, it will spin around. And now we've got a ring. So now that is an object. So now I've got the exact size of an object in that distance of what it was from the centre to the outer circle. And then if you want to, you can start using some different tools to modify, making the edges a little bit smoother. And I'll rough on whatever you want to do. So you can make them into different shapes and sizes. So this software as such therefore means that those circles that we've drawn, those shapes that we've drawn, you can manipulate them to whatever you want. And if you really get into it and have a look around some of the stuff that's out on the internet, people are literally building anything that they like with this. This is amazing, so the level of people that are building. So that's a pretty simple building a circle, so that's exciting, I know, but if you thought that was exciting, the next part is even more so. So we've got a circle with a few parts here, and this is me working on a design for an oval 8 split. So there's a few parts to this, I've sped it up obviously. So this is all just simple shapes from circles and triangles, and then manipulating them to be in the position that I want them to be. With that, I've got exact measurements in terms of exactly knowing what the centre circle is to the outer circle, and I can modify them to whatever it might be. So then I end up with what looks to be some type of oval 8, figure of 8, whatever your wording is for it, that is through a computer-aided design. So that bit of playing around took me a while to get my head around. And then after that I said, oh, but what happens if now the next person that comes through, they've got a different size finger? That would be annoying. Why can't everyone have the same size finger? But luckily enough, what you can do is just simply, go back a step, no, that's right. Just press play on that, here we go. So what you can actually do is simply go back to the very first step of drawing the design process, and change the numbers in at the very start, and then which I'm doing on this video. So those numbers that I drew at the very start, whatever the 20 odd, I'm changing those, modifying those to the new size of the person's finger, and changing the outer circle to go back to match up with this, and maintain that 3mm or 5mm in this case size for the circle. So it just shows that in terms of the process of modifying what is a splint that we've created, you don't need to go through the whole design process from start to finish. You can actually just modify a small part of it that then flows through. Ideally this will all become an automated process, so that you simply measure the outer limit of the finger, a circumferential measure, or a diameter radius, and you type those numbers in and it all automates through. So that aspect that it's just played through just shows in a second that I've modified the splint. What does happen if you've modified the splint? Here it goes again. Whenever you've modified the splint, it means the circle sizes have changed slightly, which we'll see in a second. So if the circles have changed slightly, it might mean that, say, you might need to change slightly the distances that they are. You can see they're slightly away from the triangle that holds them in position. So I just need to change that and put them back into position. That's me doing this, so that's all me doing this and having to play around with this and getting them to the right position that they need to be. There is no sort of algorithms or anything like that, which would be the next step. So a software that literally does this for you. And it means again that, that the person's finger measurement can be typed into, and then you end up with a splint that looks pretty much identical to the one that we had in the previous shot. And again, we've got this figure of 8 splint. So I'm just going to sneak back to my bag, because I've got a couple in there. I'll just pass around while I'm talking. So there's the thermoplastic overall 8 splint that I've moulded, and also 2 figure of 8 printed splints that you'll see as they come around. So you'll see the end product of that. So this is modifying a splint through computer-aided design, and interesting aspect in terms of that is how much design you can change. So really the opportunities and the possibilities to design splints, up until this point, to be honest, we've been limited by the material that we use, what we've been taught to a point, our imagination to a point. Time is always that, but really the ability to change design is significant. We can change it quite drastically, and like I mentioned before, you can actually test it out to see how strong it is or things. So there's an engineering student, Tim Gregory, who's over at Deakin, and he's made these mallet splints. And what I mean by designing and testing, he's gone and designed, he basically copied the top splint, which is a commercially available mallet splint. How good they are, it's questionable, but anyway, so that he's made that. And he's used some programming to test the strength of it. So now he's gone through and reduced the material, and the one sitting by itself with all the big holes in it has the exact same amount of strength through testing as a full splint, in the sense of essential points of strength. So they've tested out to see where it requires power and strength within that splint, and therefore can remove material. So in terms of this, what you can start thinking through this process is airflow, access to the skin for touch and precision, sensation, and also moisture content, but keeps the same result. So there is no strength loss for that splint. So again, that might open your mind to start thinking, okay, there's some splints that are pretty chunky and bold, and people take them off all the time anyway because they're sweaty and they get wet. How can we modify that to make them far more applicable to the situation and increase our compliance adherence to wearing splints? So this has just been done. He literally sent me these files the other day, and we had a look at them. So hopefully that will get published soon to show that a mallet splint can be modified to this level before it starts to lose its strength. So we can modify things quite drastically through the computer-aided design and draw them that way. The other form that I mentioned in terms of software is that actually you can use a scanning process. So you can actually scan things, and we'll have a quick demonstration of how you can scan things. So you can either draw them from a sketching point of view, like I've demonstrated, through simple circles and things, or you can scan them. So scanning's pretty expensive little devices. The spider one, the blue and grey one, we've used that one in the past, and it's a handy 25 grand. But they can be drastically, and this, like that, picks up the minor hairs on your arm. That's how good it is as a quality. What we need, probably not so much. So I've got one of these scanners, which I'll show a video of, and basically it plugs into your iPad, really power to a point, and then you scan it and you send the files around, and you can modify them. So it's $450, got it on the internet, they send it across, it's all good, had to play around with it. And this is a video of me using it. Some may have seen this video in the past. I was going to do a demonstration, but it would take a bit too long. So this is me using the sensor. Basically, you can see on the screen that the hand on the image has got a green colour or a red colour. Green means it's in focus, red means it's not so in focus. So I'll get in the way of that screen in a second. But basically, if you're asking the person to not move and you slowly work your way around the limb, or position of whatever it might be. So you can scan these and you get a fairly good take of the use of it, not too much, no contact with the person, and so forth. So from that, this is then what you can get. Okay, so this is the image, a 3D image of the limb, and with that at a pretty good detail for what we need. That you don't need to go to the how many hairs are on the person's arm, and the level of detail within that as a 3D image is pretty good. From this, that you've then got an object that you can start modifying and playing with. So again, back to computer-aided design, the mesh mixer is the type of program that I've used for this next little section. But before I do that, because I did just set these and found out recently, and just want to see if anyone, my phone doesn't do this, I don't have facial recognition. But does anyone have phones with facial recognition on it? So yeah, so you can, if you want to, look at one of those. They're all free products. And you can download Scanning Pro, is probably better. Capture's pretty good too. And you can actually do this all through your phone to nearly the same quality as what I just demonstrated on the screen. They're not quite there. So I've got a video, because again, I don't anticipate everyone's got facial recognition. From, I think for iPhones, it's iPhone 7 up or somewhere like that. Wherever you unlock your screen by looking at it, that one. Because what the screen is doing when it's unlocking is recognising your face. The same deal for these 3D images. So, just as a quick play, hopefully, there it comes. This is just a quick bit of how they do it. So this is through a phone, showing the scanning process. Here we go. And this is through looking through a phone, and it goes into that mode and whip around fairly quickly, and they start getting a 3D image of this. So this is technology that is able to then get a 3D object that you can share with people and do lots of weird and wonderful things with. They use it for social media and other social sharing objects and what have you. Obviously would look at something useful. And you can put the object in different spaces. That's a bit too noisy. So the use of phones can do this. This technology for scanning 3D objects was high-end scanners 3 or 4 years ago that cost $25,000. Now it's in a phone that people buy just without knowing it does it. So you can think the advancements in this technology in another couple of years is going to be to the quality that scanning 3D objects is going to be available in your pocket at a good enough level. If not, it's already for some of those products that are actually pretty good. So sooner rather than later, you'll be able to scan objects without too much fuss at all. So using that software, once you've got an image of someone's limb, of whatever part it might be, you can go ahead and modify it. So again, this is just a quick bit of me doing some work on a mesh mixer. So that image that you saw of an upper limb before, that was in the screen. Basically, I do, this is back to the good old day of Paint software in your Microsoft, similar sort of stuff that you can go through to there. And then you've got different tools that you can use. And again, this takes a little bit of practice, a little bit of effort, but it's not significantly. A bit of painting there. Just doing the same again. So using this software, you've got the ability to keep things from smoothing edges, you've got ability to remove parts, and you've got ability to highlight or smooth out rough edges and any spots that might not have scanned properly. Actually go through all that. I'll just roll it through to the bit where it removes a bit of the arm. It's exciting. So through this, I'm just highlighting the parts that I think might be useful for maybe a thumb spica splint, and going, okay, that's roughly about the creases that I want. Don't want to go beyond the wrist. It's very much the clinical reasoning that you would be demonstrating on a standard today. We don't want it to impinge wrist, and just get rid of all the extra little bits that hopefully are going to disappear in a sec. And with that, modify, discard that section, and we're starting to create a splint already. So by doing that, we have now got this image and this section of the part of the body that is absolute, the right position or the right measurements of that person's body, and being able to modify that to create what would then lead to these. So then we created into that aspect. We've now got an image that is the exact replica. You can even see this image is actually from that spider tech, the spider scanner. You can see the creases in my hand. So it goes to that level. You don't need to go to that level obviously for what we're creating. You could if you wanted. And then with a little bit further design, I won't take any credit for this. This was an engineer that then took it to that level. Put it in shapes, put it in branding, put it in whatever you like it. But there's principles also. So that aspect in terms of how it is done. So that process from scan through to modify and then to print then creates some of these objects. So with that, the area of 3D printing and additive manufacturing is very much, as I showed, lots of people doing work, particularly over the last year or so, but pretty much everyone's an engineer or computer design person. I thought that's good, but not many health professionals that are in this space. So I thought a better thing to do is get an honours student to help me out. So as you see through those splints that are curling around at the moment, we've got a 3D printed splint and we've got a thermoplastic splint. And what Amelia and I went through is 12 months of collecting some data, gained ethics. We were aiming for 15 people, ended up with 25 of Deakin students and staff. And the process was basically they came in for a session, did the whole consent thing. Again, I'll go into much further detail of this at the conference. But basically they came in, did some baseline measures. I did a measurement of the finger, printed out a splint as per the measurements. And I moulded a splint to the person's finger at the same time, and that was my work done, and then I left it to Amir to do the rest. So she randomly allocated them to the group. One group wore the thermoplastic splint for the first 24 hours, and then had a day off, and then wore the 3D splint for the next 24 hours. So they had a day of wearing a splint. In the measurements that we did, so in the outcome measures, at baseline we did active range of motion, in extension and flexion, we did tip-to-tip pinch, as you can see there, grip, and the Canadian occupational performance measure. And then that was the baseline measure on the first session, and then they put their splint on, whatever they were randomly allocated in, and did those measurements again, and then they put their second splint on again in that first session and did those. So we had all this direct comparison between baseline, their first splint, whatever they were randomly allocated to, and then they took that one on and put their other splint on, got the same measurements, all done within that first session. At the 24-hour mark that they were called up via phone and they completed the COPM and the satisfaction surveys in a Likert scale, looking at some questions. And as I mentioned before, they had 24 hours out off and then they put on whatever their other splint was that they were randomly allocated to. We did collect some qualitative data just to pop some comments in here or there, but didn't analyse it too greatly. So the results of all this, and again I'll go into that at a later point, but basically the starting range of motion for that splint that we're hoping for an overall of 8 splint, we're looking at that sort of holding flexion, and the thermoplastic splint was holding roughly at about 12-ish degrees, and the 3D splint was holding roughly at 15 degrees. Flexion, so how far they had allowed them to move into flexion, the 3D splint was about 85 degrees and the thermoplastic was about 81 degrees. Pinch to pinch were pretty much exactly the same. Grip strength was a kilo and a bit off. And we did analysis of this, so we looked at the normative data and saw that it was normal distribution, and if it wasn't, we used Wilcoxon's line test. All fun stats. And with that, we found these results. So basically, what we found is that for the starting range of motion, 0.05 meant that there was a difference between the groups. So if the number was 0 point something, it meant there was no difference. So for that starting point, we did see that there was a range, but clinically not a big one. Statistically, there was a difference. The 3D printed range of motion at the end point, 0.07, meant there was no difference between them. For pinch strength, there was no difference between them. And for grip strength, there was a difference between them of about a kilo mark. So we had both statistical results, but also more importantly, clinical results to show the differences or lack of difference between the two splints. For the Canadian occupational performance measure, we did the same testing, and basically the height of the bolded ones there shows that there was no statistical differences between the thermoplastic and 3D splint. Those scores you can see there. And for the questionnaire that they completed, there's lots of figures there, so I'll just jump down to the statistical significant results. So for splint comfort, there was a result that the thermoplastic was said to be a bit more comfortable. The splint convenience, the thermoplastic was said to be a bit more convenient. The 3D was more durable, and the splint water retention, there was less water in the 3D splint, so less water getting stuck into the splint, all at a statistical significant result. Appearance, there was no differences between the two types of splints. There's some that like the 3D and some that like the thermoplastic in its appearance. So that all said and done, results were basically, as a clinical factor, there's 3 degrees difference at the start range of motion between the two, one at about 12 and one at about 15 degrees. At the end point for range of motion, there's about 4 degrees difference between the two, so not too much. Pinch strength, there's 0.17 of a kilo and 1 kilo for grip strength. So pretty similar for everything along the way. The Cobham showed no real difference between performance and satisfaction with occupations, and comfort and convenience was slightly higher for thermoplastic, more durable and water resistant for 3D, equal on appearance. So all this said and done, we got to a point that we said that there was minimal clinical differences between the two splints. So we get to a point that some people prefer the 3D one, some people preferred the thermoplastic one. The aspect to produce strength and pinch and range are all pretty much the same. So then you start to ask the question, which one is better for other reasons? The aspect, the skill of someone to mould that splint, for example. So if you take that factor away, is it better that it can be reproduced exactly the same every single time? Which is another discussion. So the use of computer-aided designs opens up so many options. So everything that we do, we can actually modify on a screen and change it before we go and spend time and effort. The best thing about it is once you've made that design change, it's there forever. So that you have that same client come back and you go, yeah, that's when I remember doing something like that. There it is, pops up again, exactly. Not sort of, I made it sort of good last time, sort of bad last time. It's exactly the same every single time. So then you can modify it for another client, you can keep it in a record for what you made them, the opportunities. The amount of materials being used is also significant. So we've got materials that bend, we've got materials that are biodegradable, so environmentally is better, and we've got materials that are better for water resistance than others. The technology is most definitely getting cheaper. So again, the scanning process is on people's phones rather than needing to go out and buy something. 3D printers are, they sound like I'm selling 3D printers, but they're cheaper and they're the hydrocolators. The plastic, you get a whole reel, a kilo of plastic for about $30. I don't know how many splints that makes, but a few. And at a point, this technology will get automated. So that little modifying the splint to make it bigger or smaller will be something that happens rather than needing. The biggest thing I want and trying to push for is that we harness it and run with it rather than all those articles that are getting published in 2019 that are all done by engineers and computer designers, because that's the issue. That you saw some of those splints and things that are getting done are all by engineers and computer designers. So we need to run with it and try to be involved in whatever way that might be. So that might be part of clinical trials or in yourself thinking through technology and what it might be good. So playing around, just learning it. If you did get a chance to download the apps on your phone and literally just have play around, even for assessment based, you can scan someone's finger in a clinic just for fun and keep that on file. You might say that there are edema changes, that volume's different, anything like that. So just something to play with it more than anything. We are working towards proper clinical trials. There's some researchers in the UK and at Deakin that we're going and forever trying to source funding for research, which is always fun. But we are still pushing towards trying to keep us health professionals in the centre of this picture. And that's my whirlwind view of that thing that someone's holding. That's the 3D image of it, so I can go and change it if I like. Any questions on all of that?
How much storage do you need in computer?
Yeah, so storage is good. So basically what a 3D image is lots and lots of photos. So previously, before some nice people design good apps, what people would do is go around an object and take lots of photos of it, and then they put all those photos together to create the surface of the image, your water bottle or whatever, and that's how they put it together. So that means there's lots and lots of photos taken to get the surface view of whatever it is. So in terms of that technology need, there is storage required. that said, I've got a very fancy computer over there that did cost like too much, like $3,000 for a computer. But in terms of the possible savings that it can come to, and that runs everything in literally seconds. So I'm not waiting for things to buffer or stream and that sort of thing. It is done as soon as I press a button, it's running it. So, and that laptop is very expensive 6 months ago. It's now $1,000 less than what it was 6 months ago. So, again, technology, and so that will. The answer to your question, storage, you need lots. So you need solid drives to store information.
Yeah, because the number of clients that probably the clinics get is higher. So like storing forever the 3D splinting for the same client, that's going to imply that the person needs a huge amount of computer and huge amount of hard drive
storage.
Storage.
Yep, so yeah, exactly. So that's what people are looking at doing this for. More chronic conditions are saying that we've created this splint for you, or store it for you in your file, and then next time you come back and you've broken your splint or it's worn out after 2 years, we'll review and make sure everything's the same, but we can reprint it, modify and reprint it. But where we store that information is very important. Storage of digital stuff is extremely important. Some people are talking about providing it to the clients and giving it to them as an ownership, so they have it, and then they bring it back whenever they come next on. But yeah, very big issue. Yep.
So, I know it's probably a pretty impossible question to answer, but in your experience of being in this field, how long do you think it would take before we could all afford to start putting this stuff in our clinics, and how long away do you think that is? Is it like a 2-year process, or is it like a 10-year away?
No, I would have said 2 years ago. I got into it sort of probably about 2.5 years ago, and I'd say the technology in that time, like the printer that I bought was $1,800, and now it's under $1,000 for that printer. There's better ones than that. The material is no cost, so it's not that. The software is free, pretty much online. So it's a computer to run it, and then a printer that are under $1,000. My biggest lack of knowledge, and still the people in the UK, I was talking to them about it, is material on people's skin. And that investigation is still ongoing, because there's literally groups out there that I read one as I was well prepared this afternoon, that they did it on 25 clients in an acute setting. I can't remember a Korean country, and they've done it on clients like they're using it in their ED department. So little finger splints, the whole thing was a bit sketchy, but they had 25 people, they put splints on in the clinical ED department. My question is the impact on person's skins and things like that. Is there an impact? I don't actually know the answer. So setup wise, I think there would be an initial outlay. The biggest thing is skill of you guys having to know how to use it. But I think that learning is something, and then how far you take it is where you want to go. Versus, again, people in design and engineering are doing it to a point that they think, well, they've seen something off the shelf, they're copying it, and then modifying whatever they've copied off the shelf. So if you wanted to start doing it near immediately, you could. I don't know what the rules are for them as per thermoplastic, how much that's been tested on people's skins. People do get irritations from thermoplastics, but we'd need to delve into that a little bit. But people are already booking on clients. Was another question. Yep.
How long would it take to print out?
Yep, good question. So again, my printer's now a couple of years old and a slow one. These splints took 29 to 32 minutes as the total. So what we did for the research was we got the person in, consent to them, I measured their finger, and then I went off, changed the dimensions, press print, then I went back, they did their baseline measures, then I moulded the thermoplastic one. By the time we'd done that, the 3D one was printed, and then they could go up. We didn't have to get them in and out. But for a small, it's tiny, small splint, it was 32 minutes. Yeah, exactly. So speed for this, so the way that this printer works, I've shown in another video, is basically layer by layer. So it puts down a layer of plastic, then moves up, puts down another layer of plastic. There's so many other printers out there, so there's some that it's literally a dust bowl, and a laser heats up the spot in the dust that needs to be whatever it is, and then the dust drops away, and you're left with the object. And they're doing it in minutes, sort of thing, for objects. And they're not that expensive either. They're dropping the price a little bit. The HP ones are really expensive, but they're quick. I haven't played with one, I can't give you an exact amount. But we're talking reduction of 20 hours it used to be. We're talking small periods for small things like this.
Question from online. What is the plastic used? Is it with temperature? Can you adjust and modify it in hot water? Does it push shelf life?
Yes, good question. So this is PLA, is the type of plastic. It's high temperature, so you heat it up at the head of the printers at like 200 degrees. So you can have a go at modifying it with the heat gun. That works okay. Not great. I modify it with sandpaper, so I literally smooth it off with sandpaper. That's how to modify it. There was one of those earlier studies, they've combined low-grade temperature and plastic together, so they're creating a sort of similar to a thermoplastic they're using as a printer. So there's lots of materials out there. What I used was a basic PLA plastic. That does biodegrade with a lot of time. All good? Sorry, I was not moving expected.
Pearce, I do just have to say, just for the sake of your audience, you might remember that 2 or 3, when you just started a couple of years ago, I sent out some measurements and made one of these.
I've got that on video. I didn't want to show it straight again.
But no, she loved it.
There you go.
Absolutely loved it.
So,
I think because it was more durable than anything I had made previously. It was durable as a silver, but
And
durable.
this is someone who's been a long-term way that we've
Yeah, I have been saying it for a while. Just making good analysis.
loved joking things. So
red, exactly. I've got a video of that. I've got clicking in and out. But yeah, that's some solid telehealth right there. It's, so Hamish sent the measurements. I typed it into the computer and sent it back, and it did fit, didn't it?
Yeah.
Yeah. Of course. All right. Well, that was it. Thank you. Thank you very much.